Hey guys, so this is 18.5 through 18.10 here, talking about physics and electricity and electric currents. And as we get going into, sorry about the bell. There we go. As we get into this video and we talk a little bit about some of the stuff that we care about, one of the first things that we need to understand is why electricity is so beneficial, electric energy is so beneficial. It can be transformed into a lot of other forms of energy pretty easily. We can turn it into light, we can turn it into heat, we can store it electrically in batteries. So we have the ability to do a lot with electric energy and how we produce other forms of energy. We can turn a motor and move things. So many things that we can do with electric energy. That's why it's such a significant component of our system and our grid. But one of the first things we want to understand is that electric energy, like anything else, it is energy, and it does get used over time. And depending on the device, we have different efficiencies and different losses. And so we want to have a way of conducting or evaluating how much energy it takes to do certain things. And so we have what is called power. And we've talked about power before. It's measured in watts. We did that with, I think, other engines in the past. We talked about the change in energy over time, or energy transformed over time. In this, when we look at Q over T, right there, Q over T is the definition for current. And so the standard formula we use for power in electric circuits is that power is equal to the current times the voltage consumed. So if you can imagine going through a resistor with some current, right, so I'm going to send some current through that resistor, the power consumed in that light bulb or computer or heater, the power would equal the current I sent through times the voltage that's lost as I go through that device. So maybe I had 12 volts to start, and as I got through that specific light bulb, I'm down to 8 volts. I told me I used 4 volts going through there, or my potential difference was 4 volts, and if a current was 1 amp, I'd say I used 4 watts. Now keep in mind that wattage is not the energy, it's the rate of energy consumption. And so it's every second you're getting that many joules of energy being used. It used to be that we all had the same kind of light bulbs in our house. We used incandescent light bulbs where a 60-watt light bulb was a standard bulb, and we could compare bulbs based on their wattage, their power output. And that was roughly the same as their brightness. Today we use more efficient devices, more efficient lights, and as we do that, that same a 60-watt bulb today would be extremely bright, whereas a 60-watt bulb back in the day was just a standard-looking light bulb. So depending on the brightness of the amount of power that's being used and its efficiency, we can see visual effects through like the heat that's produced or the brightness of something. Right here you can see that if we use Ohm's law as a substitution, there are 2 other versions of the power formula. Right here, if we use it, we can produce I squared times the resistance, or we can get V squared divided by the resistance. And so there's a couple different substitutions we can use to find the power. Just any of those formulas will work though. The next thing I wanted to talk about was we talked a little bit about circuit breakers in our houses and how we typically use a 15 amp circuit on most of our house, and I'll show you those in a second. But this is how fuses work, and we used to have fuses in our homes. It was the traditional method we used for a long time. But if you look at all these different fuses, there is a thin strip somewhere in the fuse that's very thin, and when metal heats up, okay, if it's hot enough, because we let enough current flow through, these wires will actually burn up and melt and separate from each other. This is actually a method that's used for starting a fire. If you have like a flashlight with a AA battery or a C battery or something like that, and you have gum, the kind that has the aluminum foil or the foil wrappers. Okay, so if you take a gum wrapper Now keep in mind, this gets hot. But if you're out in the wilderness and you're lost and you need a way to start a fire, if you take that and you cut it or tear it so that you make sort of it's like an hourglass figure, but you want a nice long strip down the middle. Okay? So imagine all of this gets discarded and all this gets discarded. If you take the metal tip here and the metal tip here and you connect it to a battery that sits between it, right? This piece in the middle right there is going to get really hot. Well, first off, your fingers are going to get hot where you're touching the battery because you're letting current flow. So be careful. Don't burn yourself. And you don't do this for very long. You can the battery theoretically could explode. But life and death, right? Okay, so life and death, we're going to start a fire. We're going to die. That little strip right there will get really hot. And if you have something like a lot of dry grass or lint, something like that you can light, it's possible to get that to be hot enough to light a fire. So anyway, wilderness survival hack. But anyway, so very similarly, fuses are built that way, where when this gets so hot, okay, it melts away, and because that breaks right there, the circuit can't flow anymore, and the circuit breaks. Well, the problem with fuses is they are one use. Once they break, you have to replace the fuse. And if it's the middle of the night, there was a storm, and you don't have extra fuses in your house, you're out of luck. So we wanted something that was reusable, resettable, something that everyone could understand and work with a little bit better. And so using a bimetallic strip, which we learned about in first semester, we make one side out of brass, the other out of steel or something along the iron. As it heats up, okay, this is allowing the circuit to flow through the bimetallic strip into this other end. Now there's a spring right there, right? And it's flowing through, everything's great. Well, if this bimetallic strip gets hot enough, it will bend to the left. And when it finds itself into that little nook right there where there's a little cutaway, when it slips into that little cutaway, this spring is going to be able to release and push this connector rod or the switch away from the connecting or the contact point. And so because that contact point isn't in contact anymore, circuit dies. But what's really cool about it is all I have to do is come back out to my house, out to the circuit breaker, and slip this guy back into its on position, and the circuit's back inactive. So this is a reusable circuit breaker that I can use over and over again, and I don't have to worry about not having a convenient part when I need it. I think that's pretty cool. Oftentimes you're going to see all of these, all these outlets, most of your outlets in a room, well, in a room for sure, and maybe on the whole first floor or different halves of the floor, you'll have one circuit breaker that controls a lot of devices. And so as we plug more and more devices in, we're using a lot of power. If we get to a place where we've pulled too much current, obviously we want that circuit breaker to flip for us. Okay. All right, the next thing we have to talk about is the fact that while we use DC power or direct current power for things in batteries calculators, our phones run on a DC power. Most things that we want that are simple to design, we just want a DC power supply. Our cars have a DC power supply, that battery. However, it's not the most user-friendly for transportation. It's for getting it from a production facility to your home. It's also something that's it's challenging for the most part, to pack around. So we wanted something that was more convenient. And there was a big argument between the physicists and designers, Nikola Tesla and Thomas Edison. They argued back and forth about the power supply that we should use here in the U.S. Nikola Tesla won. We ended up using AC power, and we could get into it more. If you're in class, we'll have talked about it a little bit more, but it's a huge deal that we found our way using AC power. Well, what that means is that instead of having a positive terminal and a negative terminal that's always the same, we have one that alternates back and forth from positive to negative, and it's switching directions the whole time. So what that does for us is it creates a sinusoidal wave that looks like this, that represents our current or even our voltage flow from one direction to the other. When we start talking about things like average voltage or average current, we have a problem. Because when you look at, say, this point up here, say you're at 1, let's call it 1 amp. Down here, you're at negative 1 amp because you're going backwards. Well, when you start to average these currents over time, you end up with an average of 0, which doesn't help us mathematically. Everything's 0 all the time, but we know that's not true. So we had to have another way to modify and to understand the mathematics. Now, a couple of things to keep in mind. First, it's called a root mean squared, which is the square root of the average of the squared values. So first thing we do is we square all of the values. That removes any negatives from the problem. Think of it a little like reflecting this curve up here. It's not quite the same thing because they're squared, so they're bigger, but we've adjusted the values. And then we average them, and then we take the square root. It ends up putting us somewhere around here. Okay? This is what's called the RMS value. It is lower than the peak value, but it's essentially what we would call an average, or the average voltage or average current that we would see coming out of an AC circuit. If you understand the mathematics of trigonometry, you would know that based on this sine wave and its basic behavior, we ask this question, well, what is this and what is this? If you think about a sine wave, its high point is at 90, okay? So the question is, when are we hitting this average line? It's somewhere before 90, it's somewhere after 90, so it seems like it's happening repetitively around the number 90 degrees. If you use your just basic logic, the answer is that it's happening at 45 degrees. Now the root value for 45 degrees, the value we always see in the unit circle table is root 2 over 2. Now that's really just a rewrite of 1 divided by the square root of 2, and really what we're after is this root 2 value. It turns out that whether you're talking about the voltage or the current, okay, the RMS value is the peak value, we use a subscript 0 to mean peak, divided by square root of 2. Same thing with current, RMS will equal the peak current divided by root 2. So those are a couple of ways to compare what we would consider average with the peak. In the US and Canada, most of the countries like that, we use 60 hertz for our cycle time. So that means it's cycling 60 times a second. In other countries, they use 50 hertz. It just depends on what was initially set up. One thing you need to know about AC power, when you're calculating power, you can calculate it with peak values, or you can calculate it with RMS values. But whatever value you're using, you're going to get back. So if I was calculating the power usage, okay, so I say P equals IV. Okay, this is really important. If I'm using I naught, I use V naught. If I'm using I RMS, I have to use V RMS. Okay, you can't mix the peak and the RMS values, or it wouldn't make sense anyway. The nice thing about this is that the values are adjusted the same way, so it doesn't make a lot of difference. We could do it either way. But notice this is an average power. We understand it's not going to always be the same because it's always alternating. We talked a little bit about this in class, this microscopic idea. There's what's called drift speed, and then there's the actual movement. The signal, electronic signal, is going to go very, very fast, very near the speed of light. But the drift speed, you remember these guys are bouncing around every different direction. They take a lot longer to get anywhere. Let me see if there's anything else you really need to know. I think that's probably about it. There's a lot of other good stuff, but big idea, power is measured in watts. It's current times voltage. And yeah, here's your units in case you're having a hard time remembering which the units are. But good luck, guys. We'll see you in class. And yeah, get after it.